Right now, as you watch this, the James Webb Space Telescope, the most powerful space telescope humanity has ever built, is staring into the deep universe and sending back data that is forcing scientists to rethink some of their biggest assumptions. Not because Webb has proven that physics is wrong. Not because scientists suddenly have no idea how the universe works. But because Webb is revealing a universe that is far more complicated than our models predicted. And the deeper Webb looks, the stranger the story becomes. I'm going to walk you through what Webb has actually found, why some discoveries have created serious debates among astronomers, what the mysterious little red dots might be, why the Hubble tension remains one of cosmology's biggest unanswered problems, and why one distant planet has attracted enormous attention because of a possible chemical signature associated with life. Let's start at the beginning. The James Webb Space Telescope launched on Christmas Day in 2021 after decades of development. Its enormous mirror and tennis court-sized sunshield had to be folded inside the rocket before being carefully deployed in space. Unlike Hubble, Webb does not orbit Earth. It operates near the Sun-Earth Lagrange point 2, roughly 1.5 million kilometers from our planet. From there, its enormous sunshield protects the telescope from heat, allowing its instruments to operate at extremely low temperatures. And that matters because Webb sees primarily in infrared light. Infrared allows astronomers to look through clouds of dust and gas that can hide objects from visible light telescopes. Even more importantly, because the universe is expanding, light from extremely distant objects has been stretched toward longer wavelengths during its journey across space. That makes Webb an extraordinary machine for looking deep into cosmic history. When Webb began returning its first scientific observations in 2022, astronomers expected spectacular discoveries. What they did not expect was just how many questions those discoveries would create. One of the earliest surprises came from the young universe. Astronomers pointed Webb toward galaxies whose light had traveled for more than 13 billion years. That means Webb was seeing these galaxies as they existed when the universe was only a few 100 million years old. According to many models, galaxies at that stage should generally have been smaller and less mature. Instead, Webb found surprisingly bright and massive galaxies. Some appeared far more developed than astronomers initially expected. That triggered an enormous amount of research. But there is an important distinction here. These galaxies did not simply prove that the Big Bang was wrong. They did not instantly destroy the standard model of cosmology. Some early mass estimates were later revised downward after astronomers accounted for effects such as active black holes and improved their measurements. But the discoveries still exposed something important. The early universe was capable of producing complex structures remarkably quickly. And then Webb revealed another mystery. Tiny, compact, unusually red objects began appearing throughout deep observations. Astronomers started calling them little red dots. They were faint, compact, and extremely distant. At first, nobody knew exactly what they were. Some researchers proposed that they were unusual galaxies. Others suggested that their light could be dominated by rapidly feeding black holes. As more observations arrived, the mystery became even more interesting. Some of these objects show spectral features associated with active galactic nuclei, suggesting that black holes may play an important role in producing their extraordinary brightness. One of the more dramatic ideas is that some little red dots could represent a short-lived phase in the growth of massive black holes surrounded by enormous amounts of gas. In other words, they may not be an entirely new kind of star. They could be revealing a previously poorly understood stage of black hole and galaxy evolution. And that distinction matters. Science is not about choosing the most dramatic explanation. It is about testing every explanation against the evidence. The little red dots are real. Their nature is still being investigated. And that is exactly what makes them fascinating. But Webb's surprises do not stop with the early universe. There is another problem that has been troubling cosmologists for years. It is called the Hubble tension. The universe is expanding, and astronomers can estimate the current expansion rate in different ways. One method uses observations of the cosmic microwave background, the ancient radiation left over from the early universe. Another method builds a distance ladder using objects such as Cepheid variable stars and other standard candles. In a perfectly consistent cosmological model, these approaches should eventually converge on the same value. But they do not completely agree. And the disagreement is large enough that it cannot simply be ignored. For years, scientists wondered whether hidden measurement errors might explain the difference. Then Webb entered the picture. Because Webb can observe Cepheids with extraordinary infrared sensitivity, astronomers used it to examine whether dust, crowding, or other observational effects were causing problems in earlier measurements. The results strengthened confidence that the distance measurements themselves are not simply the result of an obvious mistake. That does not mean Webb has proven that new physics exists. It means the disagreement remains a serious scientific problem. And that leaves several possibilities. Maybe something about our understanding of the early universe is incomplete. Maybe something about the late universe is missing. Maybe there are systematic effects we still have not completely identified. Or perhaps our current cosmological model needs an important addition. Dark energy is one of the possibilities researchers continue to investigate. If dark energy changes over cosmic time instead of behaving exactly as the simplest models assume, it could alter our understanding of how the universe has expanded and how it may evolve in the distant future. But there is another Webb discovery that captured public attention for a completely different reason. About 120 light-years away is an exoplanet called K218b. It is larger and more massive than Earth and orbits within the habitable zone of its star. That does not mean it is habitable. And it certainly does not mean scientists have discovered life there. But its atmosphere makes it scientifically interesting. When Webb observed K218b during transits, astronomers were able to analyze how starlight passed through its atmosphere. The observations revealed molecules including methane and carbon dioxide. Researchers also reported a possible signal associated with dimethyl sulfide, or DMS, and another related molecule. DMS is particularly interesting because on Earth, much of it is produced by biological processes, especially marine organisms. That makes it a potential biosignature. But potential is the key word. A molecule associated with life is not the same thing as life. Chemistry on another planet can behave differently from chemistry on Earth. And the reported DMS signal has not reached the level of certainty required to declare extraterrestrial life. Some analyses have found the evidence intriguing but not statistically strong enough for a confirmed detection. That means K218b remains a fascinating scientific target, not proof that we are no longer alone. And honestly, that uncertainty is what makes the discovery so exciting. Because the next observation could strengthen the signal. It could weaken it. Or it could reveal that something completely unexpected is producing the chemistry. That is how science moves forward. And while Webb continues making these discoveries, another issue has emerged around the mission itself. Operating a giant space telescope is expensive. Webb was designed as a long-term mission, and its performance has been remarkably strong. But NASA has faced difficult budget decisions, and proposed reductions in funding have raised concerns within the astronomical community. A reduction in funding does not mean Webb suddenly stops working. The telescope can continue operating. But fewer resources can mean fewer observations, less staff, reduced flexibility, and less ability to respond rapidly when something unexpected appears in the sky. That matters because some of Webb's greatest discoveries were not necessarily the discoveries scientists could predict years in advance. They came from looking at something strange and deciding to investigate further. Imagine finding an unusual object in a distant galaxy and having the ability to immediately schedule follow-up observations.